Good evening, everyone. I am Dr. Soham Chatterjee from BITS Pilani. My topic is Successive Hydrogenation of Transition Metal Doped Magnesium Clusters, a Density Functional Study. Here, TM defines the transition metals. This is the overview through which I am going to present. It contains introduction, optimization of the clusters, result and discussions, conclusion, and acknowledgements. One of the most significant sources of cleaner, non-toxic, environment-friendly energy is hydrogen. And hydrogen is not a source of fuel, but it can act as energy carrier. Why hydrogen is getting attention? First of all, no emission of pollutants, only the byproduct is water and heat. High energy density of about 142 megajoule per kg. Versatility, hydrogen can be produced from various sources. Durability, hydrogen can provide a long-term energy solution as it can be produced from renewable energy sources, and also it can be stored. Where it can be stored, one of the most possible solution is clusters. So here we have chosen magnesium clusters, as magnesium cluster emerges to be the most suitable hydrogen storage material. The addition of transition metal, the addition of small amount of contaminant of the pure magnesium cluster can significantly increase the hydrogen kinetics. And but more particular, transition metal to D block elements exhibit a greater catalytic impact. Recent research indicates that the TIMG5, VMG5, nickel doped Mg4, and COMG5 are the most appropriate and most promising hydrogen storage material. In this study, our aim is to determine the best dopant and cluster size that will provide the largest gravimetric density and for the hydrogen from the clusters for the successive hydrogenation. Here, figure 1 depicts the most promising and optimized TIMG5, NIMG4, VMG5, and COMG5 clusters. Here, pink colored atoms are magnesium, where cyan blue at the leftmost is the titanium, green colored atom is nickel, vanadium is shaded as silver, where cobalt is shaded as blue. In our previous work, we have reported that titanium doped magnesium Mg5 cluster is very promising cluster for hydrogen storage, where Companion et al. Reported that VMG5 is the most promising cluster for hydrogen storage. Kalita et al. Said that NIMG4 is the most promising for the hydrogen storage cluster for in the systematic study of NIMGN clusters, and Ravi Trivedi et al. Reported that COMG5 is the most promising for hydrogen storage. Now, my question is, which one is the most capable hydrogen storage material? In order to find so, we have first calculated the electron localization function of titanium doped magnesium 5 clusters, NIMG4, VMG5, and COMG5 clusters. So the 2D ELF map can be expressed by 3 stages. First of all, ELF equals to 0.0 to 0.4 indicates no electron density or very less reactive sites of the clusters, which is shaded as blue region in the ELF map. ELF equals to 0.5 to 0.8 represents the zone with the metallic bonding, which is shaded as green region. The most crucial zone in the ELF map is 0.9 to 1, which indicates the zone occupied by the paired electrons, signifying perfect absolute electron pair localization, and shaded as the reddish region. These prominent reddish regions present in the ELF map is basically the most reactive part of the map, and these regions going to react with the hydrogen. Now, if we look at the figure 2, the 2D ELF map of the cluster, so we can see the ELF profile of TIMG5 is showing there are 4 most prominent reddish regions in the map. Actually, these 2D ELF maps are representing a cross-sectional plane where most of the reactive sites are present. Actually, TIMG5 cluster causes 5 reactive sites. Similarly, the ELF profile of NIMG4 shows 2 most reactive sites. ELF profile of VMG5 and ELF profile of COMG5 are indicates four most prominent reddish regions where the electron localization is very strong, and these regions are basically the most reactive part of the clusters, and these regions going to interact with the hydrogen. Next, we have studied the successive hydrogenation and the gravimetric density of TIMG5, NIMG4, VMG5, and COMG5 clusters using the formula given there. From the figure 3, we can see the successive adsorption of H2 molecule by the doped clusters. And there we can see that TIMG5 can adsorb up to 4 hydrogen molecules with the gravimetric density 4.54 weight%. NIMG4 can adsorb up to 3 H2 molecules with the gravimetric density of 3.73 weight%. Vanadium doped magnesium 5 cluster can adsorb up to 3 H2 molecules whose gravimetric density is 3.39 weight%, whereas cobalt doped magnesium clusters are the MG5 cluster can store up to 3 H2 molecules whose gravimetric density is 3.24 weight%. So which one is the highest? The titanium doped magnesium 5 cluster can store up to 4 hydrogen molecules whose gravimetric density is 4.54 weight%. Conclusions. So the 2D, as per the 2D ELF map, the TIMG5 has 5 reactive sites, and it can store, and from the study of the successive hydrogenation and the gravimetric density, we can see that TIMG5 has the highest number of reactive sites, and that is why it can store up to 4 hydrogen molecule with the highest gravimetric density of 4.548%. That's why it can be concluded that titanium has the highest catalytic effect and the most promising dopant, and TIMG5 is the best cluster for the hydrogen storage materials. Although the highest gravimetric density of Br TIMG5 has not met the target of US DOE criteria, which is of 5.58%, but it has been proved that enhancement of the gravimetric density of TIMG5 can be achieved by using a suitable, stable catalytic substrate. For an example, that is MgO substrate. We have already published one paper which is on the MgO substrate supported TIMG5, and we got the result that the gravimetric density is 5.628%, which is higher than the US DOE criteria, and it can store up to 6 hydrogen molecules. These are the references that I have followed. I would like to thank my co-author, Professor Sanat Kumar Mukherjee, BIT Mesra, Department of Physics, for helping me in this regard. I would also like to thank Dr. Pratisha Kumari, Organizing Secretary of INFES 6.0 2024, for providing the effective communication and providing all the important information regarding the conference. I would also like to thank all the members who are associated with the INFES 6.0 2024 International Conference from the Eudoxia Research University for providing me this nice opportunity to express my work. Thank you.